NanoHub U, online instruction.
Hey everyone, so we're continuing on how to use Camphor, which we've been covering for the last few lectures, which again is another approach to S matrices plus eigenmode formulation. And so then this is actually showing for a fairly complex problem how we can actually write some Camphor code to model the problem of what happens when light is traveling through a photonic crystal waveguide and then comes to a splitter region, which could split the light into two different waveguides. And so this is essentially defining some terminology here for basically the periodicity and the number of intermediate sections, and then basically setting up these different geometric regions within the structure. One region which has no rods, so that's basically this structure over here. And then we have a central region, which is here. We have a vertical region, which looks like this. And then we have the arm region here, where we have the two arms. And then we would basically put those all together into waveguide system, and then we would calculate the lowest order waveguide mode for this whole composite structure. And so that should tell us to a good approximation how light should propagate as it enters for a given frequency. And so this is actually the solution that we get from that calculation. And this is actually shown in the PhD thesis that I mentioned earlier from Peter Paintsman. It actually shows that for this photonic crystal waveguide splitter, that you can get split into two different branches. And you can also have very low loss, and you can quantify that loss more precisely by looking at the numerical output, but it corresponds to loss of less than 3 decibels. So that is comparable or even better than a lot of index-guided fiber splitters. And then there's another kind of problem that we can solve that's more advanced, which is for vertical cavity surface emitting lasers, also known as VCSELs, which may sound like a very obscure thing, but it's actually a very common component because it's fairly easy to make in a modern semiconductor fabrication process. And so it basically consists of a bunch of reflective layers, which are made out of distributed Bragg reflectors, and then an ultra-thin quantum well, which in this case is, say, 5 nanometers, plus another set of reflectors on the top. And what's nice about this is like you can use the cylindrical symmetry of the problem so that if it's circular, which is a very common form factor, then you can accurately solve for the modes in the VCSEL. And here we basically assume that we have two different materials, gallium arsenide and aluminum gallium arsenide, which are lattice matched. So that's why it's commonly made out of those two materials, because you get high quality and easy growth process. And so you basically would stack a whole bunch of these layers on top of each other, alternating gallium arsenide, aluminum gallium arsenide, and then plus some oxide regions on the left and right hand side, which are shown here. And then you would have basically a node that's hopefully centered like close to the quantum well. And then that would be where the mode would be located. And then you would try to find the exact mode frequency as you connect these top and bottom regions using this find mode command. And find mode is actually very useful because that allows you to not try to calculate every possible mode, but just like look at a certain subset of possible values. So it saves you a lot of computational time. And then the result of this kind of approach is that you actually get the field pattern, which is shown here kind of in this like red to blue color scheme, is primarily localized in the central region in both the radial position rho as well as the vertical position z, where you're assuming that the quantum well is somewhere around here, which kind of makes sense that it should be kind of highly localized in both ways. It's localized, of course, in the vertical direction by the distributed Bragg reflectors, but in the radial direction by the high refractive index waveguiding effect. And so this allows you to actually selectively emit only in the vertical direction, particularly if you put a back reflector, say made out of metal, on the bottom of the system. And then this is actually showing what kind of results you get for the resonant wavelength as you change the diameter of the VCSEL. So that allows you to potentially tune the VCSEL. So you can actually calculate the resonant wavelength as a function of the diameter of the VCSEL. And this is in good agreement with previous calculations from other groups. And so you can see, especially as you go to larger diameters, there's very strong agreement. And then you can also calculate the material gain that is possible in this sort of system as a function of the diameter. And you can see, of course, that like for larger diameters, the absolute gain is not necessarily as big because you don't overlap as strongly with these outer regions. But that's actually consistent with our expectations. In the next lecture, we'll talk about other things that can be done with S-matrix methods.